Good day, and welcome to the lesson 16 Day 1 video. In this lesson, we want to talk about transformations of exponential functions. Let's begin. First off, with the entry task, we're going to complete the table using the column of values from the X column, the inputs. Let's label it as such. We're going to produce a column of outputs depending on our f of x function, which will in turn be used to create g of x. G of x will create h of x, and then m of x is the creation of h of x and g of x together. We may see a pattern develop, we may see relationships develop, and we want to be aware of those happening as we just straight up complete the table. So first of all, f of x equals 2x. If x is negative 3, then we're going to take this negative 3 and we're going to multiply it by 2 to get an answer of negative 6. Take the negative 2 input, replace x in the function to get 2 times negative 2, negative 4. 2 times negative 1, 2 times 0, and 2 times 1. That completes the table of values for f of x. For g of x, we're going to take the f of x value and we're going to subtract 3 from it. So negative 6 minus 3 becomes negative 9. Negative 4 minus 3 becomes negative 7, negative 5, negative 3, negative 1. These are all increasing by 2. These are all increasing by 2. For h of x, we're going to take g of x and add 2 to it. So, if g of x is negative 9, then negative 9 plus 2 makes negative 7. Negative 5, negative 3, negative 1, and 1. Last of all, m of x takes these two values and combines them via addition. So negative 9 added or increased by negative 7 is negative 16, negative 7 plus negative 5, negative 5 plus negative 3, negative 3 plus negative 1, and last of all, negative 1 plus 1. Just some fun things that we can do with f of x as we determine what it is and then add that to another one. Okay, add it to another function or use it in evaluating the function. Today's classwork is related to the transformation of exponential functions. And as such, that tells us that we need to use technology or look at the representation of functions like 2 to the x. And so I'm going to use Desmos in order to just get a quick sketch of this first function, 2 to the x. So 2 to the power of x. So you have this little, curving line shape. If we wanted to create a table of values, clicking on the gear and clicking on table brings up the table of values. To go from 3 at 8 to 2 to 1 to 0 to negative 1, they say, or Desmos gives you the value in decimal form. I'm going to write it in fraction form. And for negative 2, 1/4. So I can plot those points on the graph. I can plot them, and from the picture of the graph, be able to, or picture of the points, be able to see that curving exponential function 2 to the x. So transferring these points to the graph space, 3, 8, 2, 4, 1, 2, 0, 1, negative 1 and a half, negative 2 and a fourth. Just make sure that it gets closer and closer to the x-axis without actually touching it. And then we should draw a smooth curve, because that's what we're seeing in Desmos is a smooth curve. We should draw a smooth curve through these points. So something that kind of goes like super flat, closer and closer to the x-axis, but increasing, and increasing even at a more steep rate until it is approaching what looks like vertical, or at least definitely increasing higher and higher and higher for the rates. For the other relationship, we're looking at 1/2 to the x power. So we'll change that in Desmos. Put the 2 in parentheses, 1/2. Maybe just delete it, kind of modify it there. And it actually is the exact flip of what we see. 3 goes to 1/8. 2 goes to 1/4. 1 goes to 1/2. 0 goes to 1. They do cross at the y-axis. -1 goes to 2. -2 goes to 4. I'm guessing -3, because it's like the flip of this pattern, would go to 8, or we're doubling, doubling, doubling every time. So now I'm going to plot them. I'm going to plot 3. I'm going to plot them from the bottom. -3, 8. And -2, 4. -1, 2. 0, 1. 1.5. 2 with 1/4. 3 with 1/8. We're never actually getting to 0, we're getting super close to 0. And then sketch the smooth curve that passes through those points. Something like so. It goes out to infinity, so I just want to draw arrowheads and sketch it so that it looks like it could continue for forever. Curve it, wrap it around. And there we have it. We have the function 1/2 to the x compared to the function 2 to the x. Both are exponentials. One shows exponential growth. The other shows exponential decay. Just to kind of lead you into it, decay, because we are decreasing as time marches on, and growth. All right. So we're diving into the conversation around what an exponential function looks like, and maybe you can recognize that if you went from 0 to 1 to 2 to 3, you would have a sequence of values of we're doubling every time. So 1 times 2 times 2 times 2. So this is still connected to that idea of what we started this entire trimester with regarding a sequence of functions, or a sequence of points produces a function. Let's turn to the next page. I'm just reminding here. So with this table, the properties of a linear transformation are also true for exponential functions. So just a quick review here, that if you have k is greater than 0, then adding a positive value to f of x is going to be a vertical shift up. If k is less than 0, adding k to f of x is going to be a vertical shift down. If k is greater than 0 and we're inside the parentheses, that means that k is positive, then we're going to shift to the left in the horizontal direction. Oh, I don't mean stretch. I mean horizontal shift left. Okay. If k is less than 0, then adding a negative inside the parentheses is going to shift the function horizontally. It's going to shift it to the right. The reason for that I'll probably get into, or I have gotten into in other videos already, but that is the big idea, is that you understand in the parentheses is somewhat backwards counterintuitive, although there is a specific mathematical reason. It's related to the x-intercept specifically, that helps you remember that when you have a positive, you're going to shift left, and a negative, you're going to shift right. Okay, if k is greater than 1, let's say the positive value of k is greater than 1, then multiplying a function by f of x is going to be a, let's see right here, right, is going to be a vertical stretch. So vertical stretch. Well, if k is less than 1, so I guess specifically bound between 0 and 1, but neither of those two numbers included, then we're actually talking about a vertical compression. Okay, what I'm saying is we're taking the function at every point and we're squeezing it down, pushing it down together. If k is greater than 1, so it's positive, then k times x, let's see, you're going to take every x value and you're going to pull it wider. Something like, I think I need to demo this. I'm going to demo this. This is supposed to be demoed with like a linear function, but we're going to get to exponentials anyway. So let's go, here's 2 to the x, and let's put in the exponent 2x. Okay. As a table for both, as a table. Get out of the way. Get out of the way. For both. Think about what these y values are. Like, where do we see a 4 in this original parent function? So purple being the original and black being the new, the adjusted. We've multiplied the x up here in the parentheses. We've multiplied the x by a number 2. It's bigger than 1. We've compressed. We're squeezing from the sides. We are horizontally compressing the function. So what was a, oops, I want to show the table. What was 2, 4 in the parent function, 2, 4 right here, we've made that number become, well, we've said actually that a 1 gets us to the same value. So we're taking the fact that its parent function gives us 2, 4, 3, 8, etc. The function as the x value, we've now taken that distance and we've cut it in half. If k is between 0 and 1, then that is a horizontal stretch. So let's just show that. Let's make this be 1/2. And now the black function, it is pulled wider. Okay, finishing the table. So when you have a negative in front of f of x, not in the parentheses, but in front of the whole entire function f of x, that's taking the function and flipping it down. Case in point, if I go back to my original function and I put a negative out there, it's flipped over the x-axis. So x-axis. And if we make the negative not there, but up in the side with the parentheses, that's where it rotates around the y-axis. Wait a minute. That function, 2 to the negative x, oh, that's worthy of a note somewhere. Note 2 to the negative x is the same as 1/2 to the x. Think about why that might be true. What do you know about negative exponents and what they do to bases? That also works whether you have a variable or you have a constant. If there's a negative exponent, whoops, okay, all right. Okay, so we're going to use the use Desmos to help answer the questions on the bottom of page 18 related to the rules for exponential functions. What do they do to transform the equation? So I'm going to start with my parent function. My parent function is 2 to the x. We can see the points that are plotted there. And let's actually use the power of Desmos to include the function notation. F of x equals 2 to the x. And that means that when we do part A, page 18, part A, this one right here, we can type in 2 f of x minus 4. So 2 times f of x minus 4. This function has been shifted down, so there's a vertical shift. This function has a 2 in the front. We're really doing this one. For part A, we're adding or subtracting a k, so we have a shift down. We're also multiplying f of x by a number, so that's a number out here. So we're doing a vertical stretch by 2 and a vertical shift down by 4. So that's what I'm going to write right here. The 2 is a vertical stretch, and the minus 4 is a, wow, they're both stretch and shift. Vertical stretch and vertical shift. Again, the goal, like in the previous one on linear, is to be able to describe what the transformation is, maybe to help you get a sense of the picture without needing to go graph it, but it's the idea related to what every little piece of an exponential function is going to provide. I also want to add in this line a rewrite of g of x. Remember, f of x is supposed to be this expression. So if f of x is that expression, then g of x would be 2 times, do a simple substitution, put the 2 to the x where f of x is, minus 4. And so we have the same equation. I can prove it, although maybe I don't need to, maybe you trust me, but I'm going to write it. Notice that blue and red are the exact same equation. Okay? Let's do part B. Part B, we're looking through the table, Maybe we're going to use Desmos, but we're looking through the table to be able to identify how f of x has been transformed, and then we'll go back and use the graph, and we'll go back and use the table to confirm, okay, that's true. When you had a 1/2, that did mean this. When you had a -2, that did mean this transformation. When you had a +3, that did mean this transformation. Here they are. H of x is 1/2 times, okay, so this is where we can use Desmos, x minus 2 plus 3. Desmos is super powerful, allowing us to even type in everything that happens in the parentheses in order to produce an answer. Let's just analyze. So I should use my mouse cursor. The function's been shifted up. Would you believe it's been shifted up 3 spaces? Would you believe that the function has been shifted? Wait, what has been shifted? Let's focus on a specific point. Let's focus on the y-intercept. So for the parent function, that's 2 to the x. For the parent function, the y-intercept is 0, 1. We're going to shift that 3 spaces up and 2 spaces, -2, 2 spaces to the right. So from here, 3 spaces up, 1, 2, 3, and then 2 spaces to the right, 1, 2. If I take off the 1/2, it should be there. Yep. So these 2 points, 3 spaces up, 2 spaces to the right. Now when I add the 1/2, this location right here where it's at a height of 4, it's going to compress within that interval halfway down. So adding the 1/2 back. Oh, it's going to snap to the grid. But the point that I'm trying to show is that the function has been transformed. First of all, let's talk about how the +3 and the -2. These refer to a vertical shift and a horizontal shift. So the whole function has been moved. But the further thing is that the 1/2 that's in front of f of x is going to, where is it at here? Vertically compress. So what were points that were so far now have become not as much growth along the way. So we have the 1/2, which represents vertical compression. Okay, let me bring up the table on Desmos and just got to reiterate that point, that the points really have been squished together. It'll be visible if I show the table, and then the table puts the dots up on the space. Let's do another table right there. Yeah, I mean, look at this right here. This gap, pretty substantial. From this point to this point, it's a gap of 1, right? From 0 to 1, the spacing is by 1. But because we've shifted, let me add another number here. Because we've shifted over 2, up 3, then over 2 is this point, and the next one over, shifting over again, is only half of an amount of space. So there's a full amount of rise over run, 1, 1, between these 2 points, but there's only half of a rise over run between those 2 points, 1/2 over 1. The vertical compression is evident between these 2 points in how much height separation there is, versus the parent function, how much height separation there is between those 2 points. All right, I want you to do letter C as extra practice. And then that'll let me move on and go to the next page. Okay, but once again, I'd recommend keeping this table handy. This table is super useful for explaining what happened in the transformation without needing to actually go graph it all the time. Or you should become more and more familiar, kind of like you're repeating with flashcards, what each of these does when it shows up in a function that's not the parent function. Okay. So next up is exercise 3 on page 19. Consider the exponential functions graph below. Which function is f of x equals 2 to the x? Well, I've already got f of x equals 2 to the x graphed right here. All we need to do is just look for something that has this shape. It has to pass through 0, 1. That's this one. And you know, not this way, but, you know, this way. So y sub 3. Okay. Y sub 3 is 2 to the x. So in order to go from y sub 2 to y sub 3, that would be this one to this one. That's a flip over the x-axis. And this table tells us that a flip over the x-axis means negative y sub 2 equals y sub 3. All you got to do is make this one, you know, which is going down, make it change its sign, so put a negative in front of it, and you've got the original parent function. Exactly this example right here in the table from page 18. So now let's find y sub 1. Y sub 1 is this function. We want to go from y sub 1 to y sub 3. That is flipping over the y-axis. And in the table, that meant the negative had to go on the inside. So if y sub 3 equals 2 to the x, then y sub 1 equals 2 to the negative x. So in order for us to flip it back around, we need to make the exponent negative negative. I mean, that's where you get your positive, and so it matches. So in order to make, you know, y sub 3 match, you need to make sure that you flip it over the x. You need to flip it over the y-axis by adding a negative to, adding specifically another negative to what's already there. That should be a 1. Okay. Not a 1, but a plus. Well, anyway, the point is that put a negative up in the parentheses with the x, and you get the function to flip around the y-axis. Okay, let's go from y sub 4 to y sub 5. Y sub 4 is this function. It looks like it's twice as tall. For instance, the parent function, y sub 3, passes through the y-axis at 1, but y sub 4 passes through the y-axis at 2. So we should probably go from y sub 4 to y sub 3. I mean, to do that, you have to, what is it? We got to divide y sub 4 by 2. And that is y sub 3. But then notice even further that to go from y sub 3 to y sub 5, that is also a cut by a half. We're not adding, we're not subtracting, we're multiplying every point. Exponentials means multiply. These are exponential functions. We're multiplying every point by a number. So to go from 2 to 1, we multiply by a half. To go from 1 to 1/2, we divide by 2. So if I combine all of these together, I would get y sub 2 equals y sub 4 over 4. Or the flip of that, I would get 4 times y sub 2. I keep saying 2. I mean 5. I mean 5. I mean 5. I mean 5. To get, because I'm going this one to this one to this one. So 4 times y sub 5 equals y sub 4. My bad. Sorry. Okay. We want to go from y sub 1 to y sub 2. So if we can connect a function to the parent function, then we're going to be able to transform it. So what do we do to turn y sub 1 into y sub 3? Put a negative up there. What do we do to turn y sub 3 into y sub 2? Put a negative out front. So this is what we could do. If y sub 3 equals 2 to the x, then y sub 1 negative equals this is all flubbing up. I'm just gonna stop and be done. What do we need to do? We need to, oh, here's an idea. So when we had the fact that we had the function flipping over the y-axis, this one right here, the other way to write that is to write it like we said on that previous page, 1/2 to the x. So y sub 3 equals 2 to the x. That's this one. We could say that this is 1/2 to the x, and this is negative 2 to the x. So to go from there to there, we first of all need to flip y sub 1 1 over y sub 1, and make it negative. This thing equals y sub 2. Well, I mean, I can tell you why maybe when I'm face to face with you, or draw it out yourself. Go to Desmos and just plug it in. If we say that we have f of x, so we can graph, you know, y equals 1/2 to the x, and we can graph another y equals, let's go instead of y equals, let's go g of x. Wait, I'm going to try something else. I haven't tried this before. Y sub 1. There we go. So y sub 2 equals negative 1 over y sub 1. It worked. Oh my goodness. This formula is exactly right there in Desmos. You go from green to purple. Booyah. I'm telling you, Desmos ceases like never ceases with me. I get more and more impressed with it every day. Can I make a diamond out of the middle of that thing? What would I have to do to make a diamond? Purple is, if I put a, okay, negative y sub 1. There we go. We got a diamond shape in the middle now. That's not what you're supposed to find, but you know what? You know I'm going to say this. Extra practice. Figure out what you have to do to y sub 2 to make it become y sub 4. And use what I did here for purple as your reference point, that I took y sub 1, which was that function, and I did, you know, I flipped it and made it negative, kind of like a reciprocal, kind of like a way to connect perpendicular lines by their slopes. Negative reciprocal to the function, and I get this flipping nature. All right, I'm good with that. Okay, I'm on lesson, the last page. This will be the last, like, you know, a couple of minutes of this video before I stop and I direct you to go to the next part of lesson 16. Explain how you would graph 2 times 2 to the power of x plus 3 plus 1 by hand. Order of operations probably is the best way to think about it. You need to shift to the left. So let's just do it in steps. 1, shift a horizontal shift left, because that's in parentheses. And then 2, following PEMDAS, push every moron down it. That's not how it goes. Please excuse, that one's so tame, whatever. But the point is that after you do the parentheses, now you have to do the multiplication. I mean, technically, yes, this is exponents, but actually it's not, because it's a function. And so because it's a function, I'm not going to focus on the exponential nature of it. I already know that I have that shape. The question is, am I that way, up, down? What am I going to do? So I have shifted to the left 3 spaces. And focus on the origin. Focus on, you know, the y-intercept, not meaning the origin, but the y-intercept, because the y-intercept is going to shift to the left 3 spaces. And then the 2, this 2 out front, depends on how much gappage, like we're going to double every space in the y value from one to the next. You know, remember when we looked at the table in Desmos? Get out of here, get out of here, get out of here, get out of here. When we looked at 2 to the x, and as a table we saw that there was 1 to 2, 2 to 4. Because we're doubling it, instead of going 1 to 2, well, come on, show me. Yep. So instead of going from 1 to 2, now we're going from 2 to 4. That's a twice as tall measurement. So we're going to double every y value. And then last of all, again, push every moron down a stair. Means that we're going to do the addition. So this one is step 3. Shift up plus 1. Okay, think of the order. Order of operations matters. So what happens inside the grouping terms is the first thing that you do. This is first. Then we go to, again, yes, it's an exponent, but in the, please excuse, in the E part of the order of operations, the E technically is not being factored into this one because 2 to the x is a function that looks like a curvy line. So the exponent's not really there as an order of operations. It's a function grouping operation. So after parentheses, then multiplication, then the addition. So 1, 2, 3. List that out for the closing. Okay, are you able to graph y equals b to the x for some growth factor b? All of my examples were 2, but if you change it to a 3, could you use Desmos or something to graph it? I can describe the effect of f of x plus k. When you add to the outside, what does that do? When you add to the inside, what does that do? When you multiply to the outside, what does that do? And when you multiply to the inside, what does that do? Please complete the table. And then I'm going to leave the exit ticket for you to do. I think that that is an opportunity for you to practice what we've talked about in order to grow, in order to become better. So you need to do the exit ticket. And then, of course, as always, do the problem set. All right, that concludes this video for Lesson 16, Day 1. And I'd recommend that you look for Lesson 16, Day 2.